And I thought maybe we could look at a little bit more of counting combinatorics. So far, you have only seen two things about combinatorics: systematic listing and the handshake problem, right? You should never look down to systematic listing because that's kind of the computation in combinatorics. So when I get a combinatorics question, I start to systematically list, and that's how I figure out what technique or what formula to use. So never feel that you're too good for listing. But today I want to go a little further and see what it looks like in practice, what they call the fundamental counting principle. It's a little over. Okay. All right. So suppose that I have 3 pairs of shoes, four t-shirts, and 2 jeans, 2 pairs of jeans. And suppose I have absolutely no sense for colors or whatever. How many different ways can I dress up? So if just anything is different, so if 2 outfits have the same jeans, the same, but the shoe is different, then it's a different outfit. So how many outfits are possible? When did anyone mock any? Just guess. All right. So, 4. Any other guess? Correct. All right. So one way of systematically listing is called a tree. Closer. So I'm going to show you a tree. The problem with trees is also going to be illustrated that they get unmanageably large pretty quickly. But suppose I dress in a weird order. I'm just going to go by the number of. So I'm going to start. The first choice is jeans. So let's say this is when I selected jeans 1 and jeans 2. And now, no matter what I did for the choice of the jeans, I'm going to go for the shoes. I have 3 options, say shoe 1, shoe 2, and shoe 3. And I have the same 3 options. And the way you read it, for now it looks like 6 different outfits. And the way you read it is you read from the start, jean 1 and shoe 2, right? But it's not going to remain 6 because now I have 4 choices for each selection that I have made. So how many little endings are going to be there when I'm done? How many little nodes at the end? These are 2 different ones. How many little blobs are going to be at the end? 14? But first of all, thank you those of you who are answering me. I ran out of space. But 24. Basically, it's 2 times 3 times 4. 2 options for the jeans. And independent of that, you have 3 options for the shoes. So if now we have 6 of them, right? 3 for each genes. And then for each ending, which would be a pair of selections, there is 4. So it's 24. You know, there we go. But I ran out of space, and that's the problem with tree. Of course, we could have listed I shouldn't have started with the tree probably. We can say, and no matter what listing we should use, we should get the same 24. We can say jeans 1, shoe 1, t-shirt 1, and then fix the beginning as much and run with the, right? We have done listings like this. Jean 1, shoe 1, 2, 4. So now we exhausted these. Jeans 1 and shoe 1 with all 4 probabilities. And all 4 possibilities. And then when we roll up, what should be the next one? If you want to be organized here, what should be the next selection? If you want to list it this way. We keep jeans 1, but now shoe 2. And jeans 1 and shoe 2 with the first t-shirt or the second or the third or the fourth. That's very much like when you're counting, and these are the digits you're rolling up. And that's just jean. So here, jean 1, shoe 3. We only have 3 shoes, so might as well. This is going to be half. Okay, so this here is, we have 3 blocks of 4. That's 12. And we're going to have another column identical to this one, except it's going to be with jeans 2. Right? But maybe it's a little bit more intuitive with trees, but the fundamental counting principle. If we can do one thing in X many ways and another thing completely independently Y many ways, then those 2 things can be done in X times Y many ways. So if we can do something X many ways and something else Y many ways, then the 2 can be done in X times Y many ways. But that involves that sort of independence. So for example, if some of the colors clash, then you don't really count every possibility. So there has to be some sort of a truly independence. And no matter what happens when I do the first thing, I still have the same number of options in the second. Okay, any questions? All right. So you will see that a lot of the things actually come up in computations, in algebra, a lot of combinatorial things. So the one question is called, it's called permutations. Is basically we have n objects, n different objects, and the question is how many different ways can we rearrange them? So permutation is the same as rearrangement. And that's sometimes referred to as the number of permutations on n objects. Number of permutations on n objects. All right. So let's start with something simple. N equals 2. So let's say we are creating 2-digit numbers using 1 and 2. How many are possible? This is not a permutation yet, because 11 is not a rearrangement of 1 and 2. So imagine that we just have one little card that says 1 and one little card that says 2, and all we can do is swap them. So in other words, repetition of digits is not allowed. If repetition of digits is not repetition. Wow, the question is going to be much longer than the answer. Repetition of digits is not allowed. Well, how many 2-digit numbers using only 1 and 2? There, these two. That's it, right? So the answer is n equals 2, 2. All right. Now, same question. I don't wanna write down this paragraph every time, but n equals 3. So imagine that we have a little card saying 1, a little card that says 2, and a little card that says 3. How many ways can we rearrange it? And the thing about systematic listing, if it's letters, try alphabetizing. That's like the most natural way of systematic. And with this one, try to do in increasing order. So just list all the different ways you can write down 1, 2, and 3, no repetition. How many do you get? Or 3-digit numbers. How many do you get? Good. Good. So fix whatever you can. So there is 1, 2, 3, and then fix 1, and then there is not much that we can do. And now we exhausted all the ones that start with a 1. So let's roll up to 2, 1, 3, then 2, 3, 1, and 3, 1, 2, and 3, 2, 1. And if you're organized, then the first one is listing them in increasing order, and the last one is in a decreasing order. And these numbers, as 3-digit numbers, they are in an increasing sequence. No one is demanding that, but the more systematic you are, the safer your method is. The devils to avoid are skipping something or counting something twice. All right, so if so when the number of objects was 2, the number of permutations was 2. When the number of objects was 3, the permutations were 6. All right, let's move up to 4 objects. Oh, but he's trying and talking to me. My previous class would just not talk to me today. So let's fix 1 and then play with the rest. 2, 3, 4, 2, 4, 3. And basically now we have to roll up 2, right? Yes, the last 24 is what I got. Yes. So the next one would be 3, 2, 4, 3, 4, 2, and 4, 2, 3, and 4, 3, 2. And so there is this thing called inductive reasoning, which is very, very favored by mathematicians because it's kind of a lazy thing, is that we're going to use what we just worked for. If you ignore this here, what you should see is a permutation on 3 items, right? How many different ways? So the number of 4-digit numbers in this case that start with a 1 should be the number of 3-digit numbers without the 1, right? So this should be 6. We just worked it out. Actually, I think the easiest to see is, let's check out the the permutations that start with a 4. Oh yeah, you've been doing this in the homework. That's why you guys are good at this. So 4 and then 1, 2, 3, 1, 3, 2. You see, this is literally gonna be the previous problem. 4, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3. Right? So we're gonna have 4 columns. Each of them has 6. 4 columns. Each 6 item. So if n equals 4, we're going to have 4 times 6, 24 permutations. Okay. So you didn't make me angry, so we're not going to list the one with 5 objects, but can you guess the number? How many permutations on 5 objects? How did you get 40? 16. So what did we have so far? That's another thing that combinatorics do is and permutations. With 2, we had 2. With 3, we had 6. With 4, we had 24. And now I'm asking you to guess for 5. Oh, keep going. And thank you for trying. Yep. Very good. So, yes, 120 is the correct answer because imagine that there are 24 items here. This is a complete permutations on 4 objects. Imagine that we make one long column out of this. So permutation on 5 objects. I'm going to write down 5 here, 24 times. And then 24 permutations on 1, 2, 3, 4. We just wrote that out, right? 1, 2, 4, 3, 1, 3, 4, 1, 3, 4, 2. So 4, 3, 2, 2, 1. So this is 24 of them. Right? We fix 5 and then the rest is the previous case. But if we write down 4 24 times, now we're going to rotate again, or we're going to rearrange 4 objects, but instead of 1, 2, 3, 4, it's going to be 1, 2, 3, 5. But it should be the same number, right? So we're going to have 5 columns. Why 5 columns? Well, the first digit could be a 1, or a 2, or a 3, or a 4, or a 5, and each column will be 24 long. Each column will have 24 objects. Because if we fix the first number, then the rest is just permutation on 4 objects, which we just figured out to be 24, right? So it's 5 times the previous one, which is indeed 120. Imagine we make a really long column, 120. And then when we move up to 6 objects, well, the first digit could be 1, and then rotate the other 5. It's right here. That's the first column. The second column, well, we can fix the first digit to be 2 and just rotate around the rest. That's the second column, 120 long. So altogether, what is your guess for the number of permutations on 6 objects? What would be your guess? Exactly, it's 6 times the previous one. In fact, we can rewrite this a little bit funny. We can write this as 2, and this is 3 times 2, and this is 4 times 3 times 2, but I just want to indicate that kind of what do we get if you just keep multiplying by a higher number. This is 5 times 4 times 3 times 2, and by the way, we could say 2 times 1 if you wanted. That really is optional. And this would be 6 times 5 times 4 times 3 times 2 times 1. And so on. So the next one is going to be 7 times this previous one. It gets pretty quick. It gets pretty big pretty quickly. 5,040. That's a lot of rearranging groups. Yeah. And this comes up a lot in algebra, as it turns out. So there is notation for this. There is notation for 5 times 4 times 3 times 2 times 1. So technically, in this definition, 1 is included. 0 never. That would just kill the whole thing. And the notation is this. So no one is yelling at you. And we read it 5 factorial. And you know where these things, you know, probability theory was developed by degenerate gamblers. Actually, that is true. And you will see that probability has a lot to do with combinatorics, because usually a probability is a fraction, like how many out of how many. Like if your math teacher is grumpy 2 days a week on average, then each day you have a 2/7 chance of your teacher being grumpy. So it's a how many out of how many. So usually the fraction, where very often both the numerator and the denominator are just a combinatorial question. Like we could say, well, so probability is just how many out of how many. Suppose we rearrange 1, 2, and 3 randomly. What is the probability that 2 and 3 are next to each other? What is the probability? Probability that 2 and 3 are next to each other. It's how many out of 6 next to each other? So 1, 2, 3, 4. 4 out of 6, which is indeed 2/3. That's it. Now you know probability. Of course, it's a little bit more complicated. The things that we count in the numerator and the denominator should be themselves equally likely. So, for example, what is the probability that I will win the mega bingo bonus, the biggest lottery prize possible, is not 1 out of 2. Either I win or I don't, right? You have to sort of list all the possible ways you can fill out a lottery ticket, and it's going to be 1 out of that. But including that consideration, it's that simple. Actually, I'm kind of interested. We didn't write out the 4. I'm interested in what the probability is on 4 objects that 2 and 3 are next to each other. So it's going to be a fraction with the denominator of 24. Same question. What is the probability that 2 and 3? I think as we go higher and higher, it's going to be a lesser and lesser likelihood, because there are much more ways to spread out. But that's just a hunch. So 2, 1, 3, 4, 1, 4, 3, 3, 1, 1, 4, 1, 3, 4, 1, and then 3, 3, 3, 3. It's good to list them all and then circle the ones that work. That's a frequent thing. So 3, 1, 2, 4, 2, 2, 1, 4, 1. What 1, 2. So 2 and 3 are next to each other. Yes. No. Yes. 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 So we have 4. It's not always going to be necessarily 4, I think, but no, no. Yes, yes. See, we don't have 4 in this column because 2 is fixed. And then we might have 2 in here and 4 again there. That would make sense to me. No, no, yes, yes, no, no. Yes, 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 yes. So what we have is 4 plus 2 is 6 times 2 is 12. So 12 out of 24, that's half, which is now less than 2/3, right? And you know, the more we go up, this problem becomes more difficult because you either have to be brilliant or just stubborn enough to list it. And sometimes what you do is you get a really nasty problem is like, okay, let's not try it with 5 digits. Let's check out the smaller cases, 2 digits, 3 digits, and then it's manageable. That's another trick. So why am I telling you about probability theory? Because I just told you about factorials, and I'm going to show you where it is in the calculator. Well, as it turns out, probability theory is every question is usually a pair of combinatorial question. How many out of how many? And so if you want to enter 5 factorial in this calculator, you write everything, you enter everything in the order you would say or write those. So we're going to say 5 first, and then we're going to go for factorial. You see that PRB there? That's short for probability. And if you click on that, there are 3 big things, and you have to toggle under the last one and push the enter to confirm. Push the enter to confirm, and there it is. So one more time, 5. And then we push the PRB button for probability. And then I'll teach you these other things too. And then you say, okay. So then factorial is already a huge number. Then it's more than 3.5 million. So if you have 10 books, 10 different books, and you wonder in how many different orders can you put it in the shelf, it's more than 3.5 million. That's pretty amazing, isn't it? That's a very, I think that's a surprisingly large number. This is also the number. If someone, you remember that when we started Combinatorics, I listed you famous combinatorial questions. So the mislabeled letters, you have 10 different envelopes, 10 different letters. How many ways can we stuff the letters into the envelope, provided we only put 1 letter in each envelope? That's this, because you can number the envelopes from 1 through 10, and then it's just a matter of rearranging things. So that the answer to that question is 10 factorial, which is pretty big. Usually in combinatorics, we're more interested in this form of the answer than this. Especially if the computations are complicated and you mispunch something, this is more meaningful for us. All right. Any questions? So what we have done was sort of an inductive reasoning, how we can use the previous case. Oh, you wanted to know how many permutations on 5 objects? Well, 5 different ways can we fix the first object, and the last 4, well, the permutations on those, we just figured out. So it's going to be 5 times whatever the previous answer was. But there is another way to look at permutations, and that's kind of neat. I'll tell you what I like about it. Let's rearrange 4 items. 4 items. Say we have little cards 1, 2, 3, and 4, and all we can do is shuffle them. We can just rearrange them. And now we're going to do something strange. a lot of the times the trick with combinatorics is to come up with the choreography. And it's a common choreography to say, I'm not going to count them all. Instead, I'm going to pretend to generate one, and I carefully keep track of how many choices did I have when I created that fictional one. So imagine that the 4 cards are here, and you're going to select one to put here. How many options do we have? If you have 4 empty slots and 4 cards desperately wanted to be picked, and we are about to pick the first item here, how many different options do we have to choose from? 4, exactly. Here, I can choose a 1, or a 2, or a 3, or a 4. And so we have 4 options. Oh, I managed the 4. Okay. Then, I don't know which one, but one of them was placed there. Now, how many options do I have for the second digit? Right, because what I picked before is gone. And what I like about this technique is that the second choice of yours is not independent of your first choice, but the number of them is still independent. Like no matter what you pick for the first digit, you're going to have the three other digits waiting there. And the fundamental counting principle tells you that you can multiply those. And then how many options do we have left here? 2. And finally, it's not much of a dilemma. We have just one option for whatever is left there standing. And that's how we get permutations on 4 object, 4 factorial of 20. So that's a completely different combinatorial argument. Now let me be a little bit, the way I learned permutations is different than the way you guys should learn permutations. The definitions are slightly different. Imagine now that we have 1, 2, 3, 4, 5, 6, 7, and we have cards, which means we have a single card with each volume. Repetition of digits will not be possible. And I'm asking you, how many 2-digit numbers can we create? And the only way this can be a rearrangement if we say digits cannot repeat. If repetition of digits. You know what? Let's do A, allowed, and B, not allowed. And I just want you to mentally ask, how many options do I have? How many options do I have? And multiply those. So we have these 7 digits, and now we just want to make a 2-digit number. All right, how many options? How many? 21. No and no, but I think you're on the right track. Here, for the first digit, how many options do we have? How many different numbers do we have a choice from? 7. And so do we the second one, because repetition is allowed, so it doesn't matter. So there are 49. If we had to list them, they would look like this. We would have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And then that's a 2-digit number that begins with a 1. And then the ones that begin with a 2, there is going to be 7 of those, because the second digit could be 1, 2, 3, 4, 5, 6, 7. So we would get a square with 7 columns and 7 rows, right? So when repetition of digits is allowed, then the answer is 49. Now, one advantage of listing them is that it might be an easy answer for the second question because you can just rule out where repetition occurs, although that's on the long run is not going to be that easy. But let's just think about it. We have 7 options for the first digit, and if repetition of digits is not allowed, how many options do we have for the second? Exactly, 7 times 6, that's 42. If you list it, then we would lose the diagonal. In this 7 by 7, we would lose 1, 1, 2, 2, 3, 3. We would lose those 7. 49 minus 7, that's how you get 4. Okay, now same question, but we're moving up to 3 digits. So we're still only using 1, 2, 3, 4, 5, 6, 7. So A, repetition is okay. And B, repetition is not okay. No, I wish I did 6 instead of 7 because it's like rolling a dice 3 times. And it's like, I like to, that's a good example. If we roll a die 3 times, one after the other, how many different outcomes are possible? Can we roll 6 twice? Yeah, of course, the dice doesn't remember what it did before, right? So, but now this is a 7-sided dice. We roll it 3 times. How many numbers can we select for the first digit? How many outcomes for the first digit? 7. And if repetition of digits is allowed, then it's 7, 7, 7, 7. We always have any digits can be used. So it's 7 to the 3rd power. Now, if repetition is not allowed, then for the second digit, how many options do we have? 6. And for the third one, 5. 7 times 6 times 5. And of course, it should be part of this 210. Okay. I want to go up to 4 digits. Come on, guys. Just guess. You can guess. All right, we have a guess there. That looks, if it's 7 to the 4th power, yeah. Good. And if repetition of digits is not allowed, oh, we can agree. 7 times 6 times 5 times 4, and correct. Okay, so I want to establish a few things. I've been teaching, oh, you don't know, you don't want to know how long. Longer than some of you are alive, I'm pretty sure. And, you know, the word choices is dangerous here. The how many choices. So I want to make, I'm just going to repeat this example. I will try to avoid the word choices because it's ambiguous. There are 2 numbers, but the question is, in this case, how many times did we make a decision? How many times did we make a choice, so to speak? How many times did we make a decision? The answer is 4 for the first digit, for the second digit, for the third digit, for the fourth digit. And both answers are structurally product of 4 factors. Of course, the factors are not the same. So the answer is 4. And then at each choice, how many options do we have? How many choices did we choose from? But now you see why the word choices is a little dangerous. So at each choice, at each decision, how many options did we have? Well, in the first case, it was always 7. In the second case, they decreased by 1, right? So all 4 times, there were 7 options, and in B, the for the first decision, we had 7 possibilities to choose from. For the second one, we had 6, 5, and 4. Okay. Now, we could roll up to 5 digits, 6 digits, 7 digits, but when we roll up to 7 digits, we have 1, 2, 3, 4, 5, 6, 7, and we want to make 7-digit numbers. With repetition, it's going to be 7 to the 7th power. That's a pretty big number, I imagine. Yeah, almost a million. 823,543. And with no repetition, is 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 is 1, 7. If these two match, then basically everything gets selected, then we're talking about a rearrangement, right? This is just a rearrangement. If we want to build a 7-digit number with no repetition out of 7 objects. Now, in my own education, this was the only thing we would call a permutation. It's basically rearrangement. But in America, I found out with surprise that this is called a permutation as well. When basically you're selecting things, everything selected previously cannot be selected, but we don't have to run out of options. So technically, this is not a rearrangement. And it's kind of weird. I think this would be P is for permutation, and out of 7, we choose 4. We make 4 selections. This is a permutation in America, not the way I was taught. And that's in the calculator too. So we're gonna say out of 7, I might be wrong, and it's 4 out of 7, we'll find out. And then you go probability, and the P and CR. N is usually the bigger one. So this should be 840. Now that's just weird. Let me swap the 2. 4 probability permutation of 7. Basically, the calculator said you cannot select 7 different things out of 4. You hit a 0 somewhere, but I'm really surprised. 7. I thought I knew. Oh, I went to under the C. Permutation 4, N is the big one. So this should be 840. There we go. So only in America, I don't know about third countries, but this is also a permutation. The way I was taught is you have to keep going until you hit 1. So it is genuinely a rearrangement. Comes up a lot in algebra. All right, any questions? Okay. So let's see, how many 4-digit numbers are there? Now, what makes this problem tricky is that we're going to make an agreement in this class that 0023 is not a 4-digit number. 0023 is 23. That's a 2-digit number. So in other words, we're going to make an agreement that numbers cannot start with a 0. And that's going to cause a little bit of excitement. How many 4-digit numbers are there? There are 10 digits, 1 through 9 and 0. But nobody's going to tell you that. You're supposed to know that or count them. So it's interesting that if repetition of digits is not allowed, then 1, 2, 3, 4, you're going to have 10 options, 10 options, 10 options, but the first digit 0 is out. So it's like this. It's 9,000. You understand why the 9? We cannot start with a 0, but then for second, and the rest is fine. And then if repetition of digits is not allowed, it's going to be even more exciting. Oh, I'm sorry, I said not allowed. Is allowed. This is when repetition is okay. Sorry. So if repetition is not allowed, all right. So for the first number, we have 9 options. 0 is out. And the second number, how many options do we have for the second number? We have 9 options again. Why? We cannot choose the previous one, but now 0 is in the game. So we lose one, we gain one. And then we just keep losing. That's it, right? This here is, we lose whatever was selected for the first digit cannot be selected, but now 0 comes in. So we lose one, we gain one. And then from then on, there is no other digits that come in. So it's going to be like that. 9, 9, oh, not like that. 9 times 9 times 8 times. And by the way, let me give you a really mean problem. How many 4 digits? How many 4-digit numbers with sum or all digits repeating? That's a very hard question, because you can have just 2 digits repeating, right? 1, 1, and then where you put the 1, 1. But that's not all. You can have 2 pairs, 1, 1 and 5, 5, and you can have a triple and quadruple. So it's not as easy as we lose the diagonal. There is a really easy way out, is to compute these two and subtract. That's the way out, right? Compute this, that's the total number, and this is the one we're not interested, but much easier to find. This is a hard question. So it's 9,000 minus 4,536, because this is the total number and this is the one without repetition. So the rest has to be with repetition. Otherwise, this is a pretty difficult question. It's a sweet little trick there. Sometimes, actually quite often, it's easier to count the things we're not interested in, and then we subtract. 9,000 minus 4,536. And if I ask you, you know, let's say 6-digit numbers from 1, 2, 3, 4, 5, and 6, what's the probability that 2 and 3 are next to each other? That's a hard problem even for me. I would have to sit down and do some counting. It's not trivial. All right, any questions? This is a new little algebra. Can you figure out what this is? Without the calculator. No, but 10 times 9 times 8 times 7, 6 times 5 times 4 times 3 times 1. And this is 9 times 8 times. See, there is going to be a gigantic cancellation, and it's just 10. In fact, this is a little tedious to write, but we could say something like, well, 10 factorial is just 10 times 9 factorial, right? Basically, we don't have to write out all this. So there is a whole little algebra dedicated to figuring out how to manipulate factorial expressions. It's kind of interesting. What about this? It's similar to the previous one. Not sure what you mean by that. So the chat box, and so the bottom one would be 20. No, it would be 20. Now I understand. Bottom one, this question, not that. It would be 20 if this says 19 factorial, but it says 18 factorial, right? So 18 factorial is at both places, right? That's going to cancel out. But to get to this, we have to multiply by 19 and by 20. And so 2 times 19 is 38, so it's 380, right? And there are interesting, this is interesting stuff. Did you know that if we multiply n consecutive integers, any of them, it will always be divisible by n factorial. Oh, n factorial. So for example, you start at 11, say 7. Our magic number is 7. It's always going to be, this is going to be an integer. If you start with any number like 201 is a nasty prime, and you multiply it by the next one and by the next one, and if you multiply 7 consecutive numbers here, doesn't matter which 7, they're all going to be divisible by 7 factorial. And it's not, I don't think it's an obvious or an easy fact. 1, 2, 3, 4, 5, 2 more, 6. This hideous product is divisible by 7. This is an integer. Kind of a cool little fact. This is touching on my I used to specialize in number theory, things of divisibility and such. All right. So we'll stop here and take the little quiz. Any questions? All righty, then I'll stop here. Thank you, guys. That was for the recording. Stop.